We'll start now. Thank you all for joining. Gemma and I are going to talk about structural identifiability of compartmental epidemic models. And to begin, I would allow Gemma to say a bit about her background in modeling.
Okay, hi everyone. I'm Dankwa Massonis. I have a PhD in applied maths, more specifically in structural identifiability and observability of ordinary differential equations. So the source of structural identifiability and how to fix it. I have also done some work in mathematical modeling, more specifically in an European project called Campus Pro.
Thank you, Gemma. And I have interest in proper inference with epidemic models and also modeling the transmission of multi-drug resistant tuberculosis. Additionally, as a postdoc here at the Center for Communicable Disease Dynamics at the School of Public Health, I co-instruct on the Harvard UGHE Mathematical Modeling for Infectious Disease Planning course, which is a course aimed to support modeling capacity in low and middle income countries. And so briefly as a plug for the workshop we're organizing at the upcoming MIDAS annual meeting, I'll encourage all of you, particularly if you do work in or with low and middle income country, please do come to the workshop on Sunday, the 29th of October at 1 p.m. happening at the MIDAS annual meeting. So today we're going to talk about structural identifiability of epidemic models. But before that, just a few acknowledgements. I would like to acknowledge some people who have been instrumental in my modeling career, and specifically special mentions to Gloria Botre, Crystal Donnelly, and Nick Menzies, who have at various times been my primary PI. Okay. So let's start by establishing the context. We are dealing here with ordinary differential equation models of the deterministic nature, and we are assuming that we observe some data and we seek to estimate a parameter, say the transmission rate. Now, typically, you will combine an ordinary differential equation model or any epidemic model of your choice, but here we are limiting it to ODE-based models, and some surveillance data within an inferential framework. And you would use this framework, say a statistical parameter estimation method like the maximum likelihood estimation method or MCMC to estimate your parameter. However, this method assumes that beta, the parameter of interest, which you seek to estimate, is identifiable. And by that, we mean that you're assuming by trying to estimate beta based on observed data and a model, that beta has a unique solution given the model structure which you designed and the observed data. However, this might not always be the case. Beta may not have a unique solution given your model structure, and the observed data may not contain information on beta. When this happens, we say beta is non-identifiable, and non-identifiability may manifest in various ways. And Gemma and I are going to walk through a couple of ways. So I'll take this example first. It's a really wonderful example by the paper by Kyle and Eisenberg. And what they do is look at identifiability of a dengue model. So on top, you see the compartmental model structure of this dengue model. And to your left, in the graph to your left, you see two fits, fit 1 in red and fit 2 in black. And these are two parameter sets that produce similar fits to the observed data. But when you look to your right, you see that although these different parameter sets produce the same fit, under an intervention, and this is the same intervention, we're removing 10% of aquatic mosquitoes from the environment. Under the same intervention, these fits give different conclusions. So on your right, you see fit 1 is in pink, and fit 1 intervention is in red, and the fit 2 intervention is in dashed black lines. And you see that these are different, although they produce similar fits to the data. So there's an issue. And when there's non-identifiability, parameter inferences might not be accurate. So I'll turn it over to Gemma to give us another manifestation of non-identifiability using a glucose insulin model.
Well, I come from computational biology, so I'm going to present a model that it's related to computational biology. This is a model that gives us a relation between the glucose intakes or levels, the insulin levels, and the beta cell mass. So in this mechanistic model, it's in panel B, we have 3 states and we have 5 parameters, but we can only measure the glucose intake. So for our output, the glucose, we can see that different combinations of parameters S, I, and P gives us the same prediction for the glucose intake. So we can not have a unique solution, and we cannot know which combination of parameters is our optimum.
Thank you very much, Gemma. So with these manifestations, we wanted to make this point before moving into the details of like how to test for structural identifiability and all of that, and how to fix it. Now, it's important to establish, to distinguish between the types of identifiability. So identifiability might either be structural or practical. So structural or theoretical identifiability is when deals with a model structure. So if the model structure offers a unique solution, or if the model structure rather does not offer a unique solution for the parameters, we say the structural non-identifiability. And now in testing for structural identifiability, the analysis really makes 2 important assumptions, among others, but it assumes ideal conditions of noise-free data and error-free model structure. While practical identifiability is dealing with the observed data. So with the data I observe, can I estimate my parameters uniquely? And it's quite clear from these that in the absence of structural identifiability, where we're assuming perfect theoretical conditions, there's no noise in the data, and the model has no errors. If under these ideal conditions, the parameter is not identifiable, then under less favorable conditions, like if you observe noisy data, which we will typically observe, then the parameter cannot be identified. And so the point this slide is making is simple. Structural identifiability is a necessary condition for practical identifiability. In other words, one would need to perform structural identifiability analysis first before practical identifiability analysis. So I'm going to walk through the options in this table. So when a model is found to be structurally identifiable, so on your left, you see a yes to structural identifiability, then we can proceed to practical identifiability analysis. There would be 2 options. The model will either be practically identifiable, in which case one can safely proceed with estimation, or the model will not be practically identifiable. That means given the observed data, the parameter cannot be uniquely estimated, although with the model structure, things are okay. In that case, one would need to determine the appropriate quantity or quality of observed data required. And Rory and Browning, those 2 references on the slide, give good examples of how to do this, how to fix and test for practical identifiability using methods like the profile likelihood or Markov chain Monte Carlo method. So if you're interested, I would encourage you to check out these references. Now, to the last row in this table, when the model is not structurally identifiable, the model is also not practically identifiable. And as I've said, think about it in this way. If in theory, that is, we assuming perfect data, which we know hardly exists in reality, but if we assume that, and under those conditions, we cannot identify a parameter, then we certainly cannot do that when we have actual data. And it has been advised that if one skips structural identifiability analysis and tests for practical identifiability, there are two dangers involved. And that's why there's just the cross sign that's saying, don't do this. If it's not structurally identifiable, don't test for practical identifiability. And surely, please don't proceed with estimation. Firstly, because you might have wrong results for your practical identifiability because of numerical issues. But secondly, because when you don't test for identifiability and you do have your parameter estimates, the uncertainty in the estimates, the sources of those uncertainties would not be clear. It would not be clear whether the uncertainty is due to the model structure or it is due to the observed data. And if the uncertainty is not clear, then it would not be clear how to fix that uncertainty, or at least how to reduce it. So we're going on to some definitions of structural identifiability, and back to the point of structural identifiability being a necessary condition for practical identifiability. That is our motivation for really talking about structural identifiability only in this webinar. But you could also look at those references if you would like to know more about practical identifiability. So we're going to focus only on structural identifiability. Let's establish the model context. So we're assuming some ODEs, and here x dot of t refers to a system of nonlinear ODEs, and x of t is the vector of time-varying disease states. So think about a vector of, say, infected, recovered, susceptible. That's what is being captured in x of t. And I would like to highlight the parameter p, the vector of parameters, and we're assuming these parameters are constant and they are unknown, and of course we'll seek to estimate that. Finally, I would like to highlight y of t, which we're assuming here to be the vector of outputs. Now, I highlight noise-free because of the point made earlier that in structural identifiability analysis, we're assuming these outputs do not have any noise, or the observations don't have noise. I would like to give two output examples here. So you can see the SIR model, classic SIR, and incidence is an example of an output, and we will express that theoretically as the relationship between the susceptible state, the infected state, your transmission rate beta, and also if you're thinking absolute numbers, and the population size. Another example of an output is the prevalence, which is the fraction of infected individuals in the population. Now, it's important to know that we use the term output and not data. Of course, these are data types, but we're not referring to observed data. We're just referring to theoretical combinations of your disease states and your parameters. Now, with this context established, we can move on to the definition. So we say a parameter pi in a vector of parameters p is structurally globally identifiable, SGI, if there's a unique solution for that parameter at every point in the parameter space. That means if I have two outputs that give me the same value, so two equal outputs, then I would expect that the parameters that give rise to those two outputs are equal if the model is globally identifiable. We also say that a parameter is structurally locally identifiable, so SLI, if a unique solution exists for that parameter within at least one neighborhood of a parameter space. So it could occur that your parameter is structurally identifiable only in a restricted area of the parameter space. So that is at other points in the parameter space, there might be other solutions, but this parameter does not have infinitely many solutions. In that case, it's structurally non-identifiable. But if it has finitely many solutions or just a few solutions, or if it's identifiable only within a restricted area in the parameter space, we say that the parameter is structurally locally identifiable. And before we move on to methods for testing identifiability, because I'm sure that's the question on your mind, like how do I make sure my models are identifiable so that I can ensure that I'm not having inaccurate parameter inferences? Before we look at those methods, I think it's important to establish the relationship between parameter identifiability and model identifiability. So if all my parameters in the model are structurally globally identifiable, then we say the model is globally identifiable. But if one parameter is locally identifiable, then the entire model is locally identifiable as well. And it makes sense, right? Because the parameters and the states describe the model. And lastly, if at least one parameter is non-identifiable, then the entire model is non-identifiable. So to the methods for analyzing structural identifiability, a lot of methods have been proposed, particularly in the systems biology literature, which is Gemma's background, but they range from very simple methods like the direct test, and the direct test employs the definition of structural identifiability, which we just looked at. So it takes two outputs and seeks to determine whether with the same output we have like the same parameter value producing that. So you can test for that using algebraic methods, but there are more complex methods like differential geometry and differential algebra based approaches. Now with that, it's very difficult to test by hand, particularly if your model is complex. And so just in order to like avoid all that complex math, there's good news. These methods, at least some of them, have been implemented in software toolboxes, and there's a range. We've put references in for them. Today, we're going to focus on two: CIAN, which employs the differential algebra and Taylor series approaches and is web-based, so you could put in a URL. It takes you to an interface, which I'm going to show briefly now, and you can test the structural identifiability of your models. We'll talk about limitations later, though. And Stride Gold, which was developed by Gemma's group, which is based on differential geometry. So first, I will talk about how we use CIAN in our study on structural identifiability of common epidemic models. And then Gemma will talk about how they use Stride Gold in studying the structural identifiability of COVID-19 models. So that's what will take us to the end of the talk. So first, our study. So together with Crystal at Oxford and Andrew in Michigan, we wanted to think about how output types influence the structural identifiability of model parameters. And what we did was to sample a range of really common epidemic models. Many of you are familiar with these. So the SIR, the SLIR model, which you might employ in diseases such as COVID-19, where the latent period is non-negligible. And so there's a need to actually account for that. The SLIR kill model we refer to kill as the remission state, which you'd like to use in models like for hepatitis A transmission, where there is a very significant period of remission before relapse. And lastly, a vector-borne disease model, which you can use for malaria or dengue. And to the right, you see some output types we considered. again, aligning with really common data types we use in epidemic modeling, like incidence, prevalence, and for the vector-borne disease model, detected vector counts. And what we did here was to combine these models with different output types and test whether the combinations of these models were structurally identifiable. So just to give you a peek into the actual equations and what we were calling output. So again, you saw the example for the SIR and also the SLIR model. I'll just want to draw your attention here to the SLI model, which was used for, which we were considering could be used for a vector-borne disease. We considered 4 different data types or output types for that. So incidence in hosts, prevalence in hosts, incidence in vectors, and detected vector counts, where people go out and put out traps, for example, for mosquitoes, and then we'll count these vectors. So with this setup, we tend to CIAN. So CIAN is a publicly available web-based toolbox for testing structural identifiability of parameters. So I'm going to stop here and just show how you can use CIAN to test the structural identifiability of your model. So I'm going to stop sharing my screen and begin sharing another screen for CIAN.
Emmanuelle, there's a question in the chat, and I just wanted to know if you prefer to take questions live or if you want people to hold their questions to the end.
We would like people to hold their questions to the end.
Okay.
I'm sorry, I have answered the question.
Oh, great.
Okay,
so Gemma is also working on that. Thank you so much, Gemma. Please don't be sorry. Okay, so I will reload this page. So you can see here the CIAN toolbox, and what you will find in the interface first are examples of, can you see my screen? Yes. Okay, examples of the papers that explain the math behind these the CIAN toolbox method. And when you scroll down, there's a box here where you can insert your model. And when you click on determine, it gives you the results for the structural identifiability of your parameters. So I will go right here and copy the CIAN friendly input for the SIR models we tested. So I would just like to highlight that here we have made available all the inputs we used in our paper. So when you do come to the GitHub page that's linked in the paper, you would find this and you would find all the inputs we use. So just using the SIR and the output type as incident for an example. So when we come back to CIAN, I will paste here my input. So this is a differential equation for the susceptible state, the infected or infectious state, the recovered state. And here I'm assuming that the output that I will observe or that I seek to measure is incidence. So just written as a combination of the parameter beta and the disease state. So when I click determine, we see CIAN is doing something here. So we scroll down and we find the results. So globally identifiable parameters are in the green rectangle here. We see that there's no locally identifiable parameters, but there are non-identifiable parameters. The initial condition for my recovered state, which here I'm also assuming is a parameter. I don't know how many people are recovered by time 0. And also the transmission rate is non-identifiable. So we can see that under the simple SIR model, if the output you're working with or the data type you're working with is only incidence, then your transmission rate cannot be identified, at least structurally. And one will need to do something else to identify that. So I'm going to stop share and start to share the presentation. Great. Can you see my screen?
Yes.
Wonderful. It's good. That was seamless. So let's go to the results. I've shown you what our method is. Now, what results do we have? So you see the first column in this table represents the model structure. So all the model structures we had mentioned, SIR, SLIR, and the rest. And the second column represents the output. I here is incidence, P here is prevalence, and H is human data. Now you can see just like the results I just showed in the first row for SIR, that for the SIR model, our parameter beta is not identifiable. Also, but under prevalence, this parameter, is identifiable. And so we see that when we do change the type of output, it affects the structural identifiability of parameters. And that was the main point, really, of our study, that it's important to think about the kind of output you're considering and the kind of model structure, because that combination really influences the identifiability of your parameters. We can see, for example, with the vector-borne disease model, that with human data, the model is not identifiable. So there are a number of parameters that are not identifiable given human incidence or human prevalence. We considered multiple outputs. So what if we don't just have one output and I'm using my output as both incidence and prevalence? Then I see that all parameters become structurally globally identifiable. So again, the main point is when you're thinking about estimation, it's important to think about the output type, but B, is important to think also about whether you can combine several data types, because we found in our study that the more the data types, the more identifiable your model is. So I'm going to turn it on to Gemma to talk about her study on COVID-19.
Okay, so what we did is like a tutorial article. So we studied multiple models that were applied during the pandemic, and we studied the structural identifiability and observability. What does it mean that a model is observable? So observable is the same as identifiability, but for states. So if a state is not observable, we cannot predict it. So going back to the example that I have presented at the beginning of the talk. So this model of 3 states is neither identifiable or observable. How can we know that our model is not observable? Because for each different combinations of parameters Fi and P, we get different predictions for our state of the insulin levels. So this is a manifestation of a structural unobservability. So in our study, we create a database, and we study the structural identifiability and observability using a StrikeCall. StrikeCall is a MATLAB toolbox that maybe if you see these screenshots, it can seem that it's so difficult to do it. But once you get used to use a StrikeCall, it's easy.
If I could interrupt real quickly, if you could move your mic a little bit further away from your mouth, there's still some air hitting the microphone.
It's better that.
That sounds good there.
Okay.
Thank you.
So In the right, you have the script to define your model. So you have to define your states with vector X, parameters with vector P. H is going to be the output of your model, and F will include the dynamic equations. Also, if you have your initial conditions, you can put it there. Then you have to run the main script that it's called a stride call, and you will get an output. That's a result summary that gives you the unidentifiable or identifiable parameters and observable or unobservable states. So we have done a study of this for each of the COVID-19 models. So I'm going to present an example of a model that it's not a structural, identifiable, and observable, and how we can manage to fix it. So we have this model that is susceptible and factory recovered with 3 additional compartments: A for symptomatic, Q for quarantine, and I for isolation. So this model, we can only measure 2 outputs, and if we do our study, we see that we only have 5 identifiable parameters and 2 observable states. But our goal is to predict a state S that is susceptible, but this state is not observable. So what can we do to manage to predict susceptible states? Well, the first one is to include more outputs. Imagine that we can measure the state of infected because we can distinguish between asymptomatics and infected. So adding this additional output, we see that we get 6 more identifiable parameters, and the state S is right now observable. So we have accomplished our goal. And another way to gain identifiability and observability is decrease the number or the dimension of our model. For example, leaving out the compartment of asymptomatic people. So the observable state is the susceptible people. So we have already accomplished our objective. The third option that we have to gain observability and identifiability is simplify the parameterization of the model. So in this case, we have decreased the number of death rate. In order to have 6, we have passed to 2 different death rates. So simplifying this parameterization gives us 4 more identifiable parameters and 1 additional observable state that is a susceptible one. And the last one, and this may seem counterintuitive, is that considering time varying parameters, for example, the transmission rate, that it could depend on the season, if we are on summer or if we are on winter, give it the dependence on time. So this in some cases is going to give us a better identifiability and observability to our model. And well, that's the 4 ways in order to fix the identifiable and observability issues that our model could have.
Okay. Thank you very much, Gemma. So this really summarizes what Gemma has explained, and the first way that we have emphasized here is about adding more outputs or changing the types of outputs that one might consider. Also, with too many states or parameters, you might think about the possibility of estimating a parameter when you have about 16 states with just incidents, right? Like with that many parameters, one cannot be sure that the incidence output contains much information to estimate all those 16 rate parameters. And she has also talked about simplifying the parameterization. And one thing that we would like to mention here is about identifiable combinations. So in the literature of identifiability, we say a combination of parameters is identifiable if separately the parameters are not identifiable, but when they are combined in a kind of linear or non-linear form, they become identifiable. A classic example is the beta parameter, the transmission rate parameter we mentioned earlier. In models where beta has not been identifiable, it has been seen that sometimes multiplying beta by the detection rate can make that combination identifiable. So that's an example of an identifiable combination. And also lastly, as Gemma explained, instead of constant parameters like beta, considering beta of t, where beta changes over time. Now, what are some challenges in testing structural identifiability? I think the first challenge, which is not stated here, is that the math can be quite complex. Thinking about differential algebra or differential geometry. So people who might not have a background in testing in differential algebra-based methods might not readily be able to apply to their models. And although those software toolbox exist, it's important at least to have a fair understanding of the underlying method so that one can interpret properly the results from this toolboxes. Again, with the available toolboxes, the software does not easily scale for complex models. So in our study, we were testing models that had about 9 states, and we found that with some other toolboxes, it took even more than a day to get results. So in those contexts, we see that there's difficulty for the toolboxes to scale up, for some toolboxes to scale up for complex models. Also, there are only few extensions to stochastic models. I mentioned in the beginning that our context is deterministic models, but we all know that deterministic models do have their limitations, and particularly in the early stages of the outbreak, when only a few people have been infected, stochastic models are preferred. Now, the methods for stochastic models have not been established as much as the methods for ODEs. However, there's this really good paper which I highlight here. It is a review. So if you're interested in how you can think about transforming the methods for ODEs to stochastic models, Browning and colleagues do a really good job at that. So I'll refer you to that. In conclusion, we have talked about the what, the why, and the what can I do next. So the what is a structurally identifiable model. It's a model in which all the parameters can be uniquely determined given the model structure. Why is it important? Like, why would you need to test for structural identifiability? Well, a non-identifiable model, as we saw in those manifestations, might lead to inaccurate inferences. And what can you do next as an infectious disease modeler? You could explore those tools. CIAN is web-based, it's free. So you could check that out. You could also check Strike Gold if you're more MATLAB-based. Not only do these tools give results for identifiability of your parameters, they also provide clues for fixing non-identifiability. So for example, CIAN also has functionality for suggesting identifiable combinations. So which parameter combinations which parameters you could combine in order for your models to be identifiable. And with that, would like to thank you all for your attention and take any questions. Thank you.
We do have some questions up in the Q&A if you wanted to get started on those.
Yes. So maybe the first model and Gemma, the first question, sorry, and Gemma, the second talks about time varying parameters. So you could take that. But the first question from Katrina is, what if the most relevant model is not in your possible list? Not sure I understand. What if the most relevant model is not in your possible list? I'm not sure, Katrina, can you come again, please? When you say possible list, do you mean what if the model is not, what if your relevant models are not identifiable? Is that what you mean? If you could rephrase it, that would be great. And the second says, thank you for a great presentation. Can you please explain why having a time-dependent beta can help? And I'm assuming that you are referring to a beta T, which, for example, can be due to seasonal forcing or school vacation schedule. Yes. So can you take that, Gemma?
Yeah, of course. So as Emmanuelle said, sometimes you have identifiable combinations of some parameters. So in the example that I have presented, the product of these two parameters is an identifiable combination. So if this product is always, for example, I can't remember the exact number, but imagine it's always 3. And if you put some of these parameters as a time-varying parameter, cannot give the same product. So if you have a time-varying parameter and the other one is constant, then you will not always get the same number of the product. So you are going to break this kind of compensation that exists between these two parameters. So if you break this kind of relation of compensation, then you will gain identifiable parameters. So the main idea of why it can help, it comes from the constant compensation between them.
That's great, thank you. And there's another question that says, what about doing the fitting to the data? Okay, that question is taken off, but okay, I'll just go to questions I can see now. Can structural identifiability be applied to mathematical models that are not calibration with epidemic data set? Okay, so I understand your question as, and please tell me if I'm wrong, that can we think about structural identifiability in the context of models that are not being calibrated to any data set? Well, it depends. If you're calibrating the model, if you're not calibrating the model but are doing predictions, then it's important to ask upon like what values of parameters are you using in the predictions. If these parameters are from like other models, then it's important to think about have those parameters being estimated in a way such that they are structurally or structurally or practically identifiable. If you're sure, say from expert knowledge, you're very sure about all of the parameter values, then yes, you could go ahead and perform and forecast, but we're talking in the context of calibration. So another question is, determining output is dependent on the data available. Is it correct? If yes, choosing a different output is not always possible. Is it correct? Yes, it is correct. Yes. So the output is dependent on the data. And yes, you might not be able to choose a different output if you really do not have the data to estimate that. Yes, Katrina, please talk if you can.
I just allowed her to talk.
Just wanted to ask, so what I mean is if you have, you know, a set of models that you're putting into your package there, and you didn't put in one of the structures that actually is most relevant, how does the process work? So the example you gave was one with SIR, SLIR, SLIRQ, for example. What if you hadn't put in the SLIR model as a possible structure, and yet that was the most relevant? What happens when you analyze? Because this is about inferring pattern from process, right? This whole method.
Yes.
Am I correct?
Yes, you are.
Yeah, so what happens if somehow you haven't considered the model that might be the most relevant to the actual dynamics? Like have you tried something where you generate data from a known model and then try to recapture it, for example? And I'm misunderstanding you, but I think that's what you're trying to do, and I'm trying to understand what happens if you haven't thought of something.
So thank you for your question, and Katrina, please let me know if this doesn't answer your question. But the assumption is that each of the models you design, you believe are relevant to the problem. So you have a model, you have your data, and you are ready to go ahead with estimation. That is the context in which we're talking about, and we're not necessarily talking about like trying to choose from different models, although of course, if one model is not identifiable, then you would want to tweak the model by adding another output or changing or taking away some states. If the relevant model is not structurally identifiable, then you would want to use the methods that Gemma walked through. So taking away some state, changing the parameterization, adding some outputs in order to get at least a model that is close to that which is relevant, and that can explain the mechanisms you observe. Does that answer your question? Please feel free.
Yes, thank you. It might be fun to talk more later, but
okay.
Thank you for now. Yes, thank you.
Yeah, thank you. And there's another question from Bren. Can structural identifiability ever depend on the observation time points? Example, observing just the beginning stages of the epidemic versus past the peak. Do you want to take this, Gemma?
Yes, so the basis of structural observability assumes that you have infinite time points and that they are noise-free. So structural identifiability does not depend if you are trying to predict or calibrate your model with the first beginning steps of a pandemic, for example, versus the past of the peaks. However, if your model is locally observable or identifiable and not global, yes, it would help, because normally you are losing some kind of identifiability and observability near initial conditions. So maybe changing the initial conditions could help to gain more identifiability and observability. But you are always assuming that you have infinite time points and noise free.
Thank you. Thank you. Any other questions? So there's another one. In practical epidemiological research, how does the lack of structural identifiability impact parameter estimation and model validation? Okay, so I'll take this in Gemma if you want to add. So we did, in fact, in Gemma's second example of the manifestations of non-identifiability, we didn't go into what type of identifiability that was, but that was structural non-identifiability. And you see that when you do have a structurally non-identifiable parameter, you will, in your predictions, have just different trajectories for things that really fit the data quite well. So how does it impact parameter estimation? It has the potential to lead to wrong outcomes or inaccurate outcomes, both for the mean value, but also for your uncertainty. Gemma, do you want to add anything to that?
No, that's a point. So when you're trying to estimate parameters that are not structurally identifiable, and in a model that it's neither observable, so each of the different conditions, each of the different combinations of the parameters that correctly fits the data and gives you a loss function, for example, and you take this result in order to predict an outcome and see, okay, so maybe if we start the vaccination before we can reduce the infected individuals, if you have a bad combination of parameters, you are not going to be able to correctly predict this forecast or this prediction that you are trying to do. So it's not only for the parameter estimation, but also for the prediction of the states that you can not directly measure, but that are in your model.
Okay, thank you. There's another question on what about doing the fitting to the data with ODs and then using the stochastic version of the ODs for forecasting. So if say the OD is, and I assume here by your question, you mean the OD, you find that the ODs are structurally identifiable and of course practically identifiable, and you do your fitting and then you use the stochastic version of the ODs for forecasting. I would say I really don't know what you mean by stochastic version, because one might define that in different ways. Are you talking about just having the stochastic version of the model parameters, or you're having like the stochastic version of the states, etc.? So I'm not sure what you mean by stochastic version, but as long as the parameters are identifiable with the ODs, what we can say is they will be, at least you have the minimum condition for having correct inferences. If by changing to a stochastic version, the model structure changes in a way that affects, say, symmetries in the model, then we cannot be assured that your model will be identifiable. Would you like to add anything, Gemma?
There is a paper that was published, I think that last year, that talks about how to transfer the information of structural identifiability of ODs to a stochastic version. And in fact, it happens in the other way. So sometimes stochastic models has a higher rate of structural identifiability than ordinary differential equations. But maybe you can not apply always that projection between one another, because you, as far as I can remember, you have to be in some conditions of not losing energy in your stochastic version. So be aware of doing that, and I will suggest you to double check the structural identifiability.
Yes, please. And one paper also that's similar to what Gemma mentioned is this paper by Browning, like thinking about how to move from an OD. So they moved from an OD to like an SD type model for SRL. So please do check this paper out.
I have a question, and it may be naive, but let's say you choose not to employ structural identifiability analysis, and you go ahead and do your fitting for your parameters, etc. Are there any clues in performing your fitting and parameter estimation where it's very clear that you should be doing some identifiability analysis?
Yeah, so the first clue, and I mean, that was my introduction to identifiability analysis in my first year in my PhD, working on a hepatitis A model. I was fitting the transmission rate beta. I found that whenever I did fit and I changed the manual bounds for the MLE, my range, like my estimated parameter bounds, just aligned very well, always with this new bounds for the MLE. And I wondered, like, why is it that my estimates are just aligning with my manually set bounds? And that was a clue that my transmission rate parameter was not identifiable, and we needed to redefine it before publishing the paper. So that is an example. And another clue, as we gave earlier, is like thinking about the manifestation of non-identifiability here. So if you do change your parameter value slightly, and that leads to a really large change in the predictions, that can also be a clue.
Great, thank you.
I don't see any additional question, Kristen.
It looks like there is one, but we do, for the sake of time, I mean, I think you can answer this one quickly, but because we're at the top of the hour, we'll need to be ending the webinar. But you can go ahead and answer this. And then if you guys want to provide your email addresses in case anybody has any further questions, feel free to do that. We'll have this presentation up on our YouTube website too.
Yes, thank you very much. So yes, we're happy to provide our email addresses, and we'll be happy to talk about this. I mean, thinking about the advances in structural identifiability lately, I think an easy to use tool is CIAN, which we just highlighted. And indeed, the challenges about not being able to scale up to complex models are really opportunities for more research in the field. So yes, more remains to be done. Thank you.
All right. Emmanuelle and Gemma have provided their email addresses there in the chat. I'll give you guys a few seconds to write that down. And then we'll go ahead and end the session. Thank you so much for a wonderful presentation. I think everybody enjoyed it.
Thank you.
All right.
Bye.
Bye, everybody. Thank you very much.